Hi, my name is Eric Bogatin. I'm a signal integrity evangelist with Teledyne LeCroy. In this second of 3 videos, I'm going to walk you through some of the innovations the WavePulsar 40iX introduces that enable complete time-domain characterization of high-speed interconnects. In the previous video, we looked at S-parameter or frequency domain characterization. What we're going to find is that while we often refer to the time domain characterization as TDR response, there's so much more information available in the time domain if we dig a little deeply, and that's where some of the features of the WavePulsar 40iX come in. One of the innovations introduced in this instrument is the integration of being able to look at the same response of the interconnect described in the time domain or the frequency domain. In the previous video, we focused on the frequency domain analysis, and we saw that while we could gain valuable information looking at the single-ended or the mixed mode response, there were still some insights to be gained that were a little hard to get in the frequency domain, where the time domain can get us to that answer a little bit faster. And that's what we're going to take a look at. It's really the integration of both looking in the frequency domain and the time domain that can give us that complete understanding of the properties of the interconnect. And in the next video, we'll take a look at some of the features in the deep toolbox, such as de-embedding and the ability to do a full channel simulation by taking a PRBS signal, sending it through that channel as described by the S parameters, and looking at the response in terms of an eye diagram to allow us to quickly analyze how well will this channel behave in a real system simulation. We're going to once again use that differential pair that is part of the evaluation board that shipped with each WavePulsar 40iX. Let's take a look at its response in the time domain. As you can imagine, when we take a look at measurements of our device with 4 ports, there's a lot of information available to us. That's where I think it's really important to organize the data in a way that makes sense, that we can analyze quickly. My own personal preference is to show frequency domain response on the left-hand side and time domain response on the right-hand side. Initially, we're going to look at the single-ended response, and then we're going to look at the differential response. In the previous video, we looked at the S parameters in the frequency domain. Now we're going to look at the time domain response, and that's displayed over here on the right-hand side. So remember our device. It's a 4-port interconnect composed of 2 single-ended transmission lines with coupling or 1 differential pair. When we look at the single-ended response, we're analyzing this structure as 2 single-ended transmission lines with coupling. In the upper right quadrant, I've placed all of the time domain reflection signals, and that corresponds to the diagonal S parameters S11, S22 in the frequency domain. Now we're looking at it in the time domain. Let's take a close look at that response. We've sent the step edge in, we've looked at the reflection coefficient, and we've automatically converted that to impedance profile. So really the TDR response is the impedance profile the signal would see as it propagates down that interconnect. Only because it's 4 ports, we get 4 different TDR responses. Now we would expect this interconnect to be relatively symmetrical. Each of these 2 signal lines are pretty similar, and they should look the same from port 1 side or port 2 side, or from port 3 or port 4. And so all 4 of these TDR responses should look pretty similar, and sure enough they do. We note, however, there are 3 important features in the TDR response. The first is it's not a uniform transmission line. It's not the same impedance from one end to the other. In fact, there's a large impedance discontinuity. We start out at 50 ohms, but then in the middle we raise to a much higher single-ended impedance, almost 70 ohms, and then it drops back down again. What's the feature in the interconnect that causes this behavior? This particular differential pair was designed for a constant 100 ohm differential impedance. When the traces are far apart and uncoupled, the differential impedance is 100 ohms, and the single-ended impedance has to be 50 ohms, and that's what we're measuring in the single-ended TDR response, 50 ohms. But when they're tightly coupled, if we had just brought the 2 traces close together and kept their line width constant, that differential impedance would have dropped way down. In order to keep that 100 ohm differential impedance profile, we have to decrease the line width of those traces. We make them narrower. And as single-ended transmission lines, a narrower line means higher impedance. And sure enough, we see that as almost a 70 ohm instantaneous impedance down the length of that line. And again, when they pull apart to maintain that 100 ohm differential impedance, when we designed the interconnect, we increased the line width in order to maintain the 100 ohms to make it 50 ohms single-ended in the uncoupled region, and that's why it drops down. That's also why we see the big ripples in the return loss, because we have this very large impedance discontinuity. Very large return loss, very large impedance discontinuity in the time domain. And now we see where those two discontinuities come from. They come from the two ends of the coupled region, this region and this region. The second interesting feature is the source of the resonance for port 2. Remember, when we looked in the frequency domain, we said, gee, they all have a very similar return loss except for S22, and it had this large resonance at around 30 gigahertz. Port 2 is over on this side, and so we're going to zoom in at the TDR response to see if we can find out any more information about that resonance at port 2. So we're going to zoom in on the TDR response here, and now you can see the scale. We're at 1 ohm a division, so we've really zoomed in a lot. And you can see that port 2, of course, is the red trace here. The others, pretty constant, within roughly about an ohm up and down that region where they're uncoupled. But the reflected signal from port 2, you can see has some clear resonant structure in it. There's something that's ringing there. Exactly what, I have to say, I looked closely with the microscope. I could not tell what that structure was, whether it was something related to the connector or the launch region. But there's something in this region that's resonating. As that edge goes by, it excites that resonance, leaves a little bit of its resonant energy in its wake, and it bleeds back as that signal travels on. And you can see that decaying resonance as the signal continues heading on. It's probably some structure around here, just can't tell visually what it is. We'd have to delve deeper into the design features and maybe even do a cross-section to see what that structure is. My estimate is a 30 gigahertz structure would resonate if it was something in the order of about 25-30 mils in size. And so that's the kind of feature that we're looking for that might cause that sort of resonance. The other launches don't seem to have that resonant structure to them. Let's go back and look at the complete TDR response. The third structure that I see in the TDR response is a slight increase in the impedance as we go from one side to the other. Now, if there was a real impedance change in the line, that is a real structural feature that caused the impedance to increase as we go down the line, then I would expect when I look from port 1, I'd see the impedance increasing. But when I look from port 2, I'm starting on the high impedance side, I'm going to see the impedance decreasing. And so we would see a different behavior looking in port 1 than port 2. That's one of the advantages of being able to look at all four of the ports at the same time. When I look at the TDR response, I see that looking from port 1, it looks like it's slightly uphill, and looking from port 2, it looks like it's slightly uphill. That's a clear indication. The fact that it's uphill in both directions is a clear indication that we're seeing a small series resistance down the interconnect. So that is what accounts for that slight increase. So the three features I think we understand. The high impedance in the middle because we have a narrow line, the slight resonant structure on port 2, there is some structure clearly that is resonating, that's a very small physical size, and the slight increase in impedance due to the series resistance. So we gain a little bit more insight looking in the time domain than we did in the frequency domain. Now let's take a look at the other terms in the time domain, the transmitted signal and the crosstalk terms. And those are down on the bottom. There's a lot of data here, so let me selectively turn them off so we can look at them one at a time. The first term we're going to look at is the transmitted signal, the time domain transmitted, TDT. And this is, of course, the S21 signal. We send the signal into port 1, we look at what appears down at port 2. And you can see the time delay in going in and coming out is about a nanosecond or so, based on the 6-inch path length for the interconnect, but you see there's a little bit of distortion in the transmitted signal. It's roughly a 1 volt signal goes into port 1, and we're seeing the signal coming out on port 2, and we see the distortion. Why is that? Well, remember when we looked in the frequency domain, we saw that large insertion loss dip at around 8 gigahertz, and we saw that that was due to the fact that we send energy into port 1, and we have a lot of far-end crosstalk that comes out on port 4, and that robbed some of the energy that would have come out port 2. Of course, it's microstrip, so we would expect to see far-end crosstalk, and the signature in the time domain for far-end crosstalk is to see a large negative dip corresponding to the time delay coming out and roughly the rise time of that signal. Let's take a look at the far-end crosstalk, the S41 term in the time domain. So we'll turn on S41. And sure enough, it's exactly what we expect to see in the time domain. It's a large negative dip, and just think about the numbers. The signal coming out is only a 1 volt signal, and the far-end crosstalk on this scale is almost a 400 millivolt signal. It's a huge amount of far-end crosstalk. Now we see why we have the distortion over here, because we've taken some of the energy out of the signal coming out on port 2, and now it appears in port 4. And so we've distorted the signal coming out on port 2 and put that signal into port 4. But now you can see another puzzle. In the far-end crosstalk, we have this little flat region over here. Why do we have this signal coming out over here? What's the cause of this behavior in the time domain? When we look at the complete electrical properties of our 4-port interconnect, we have to also include the near-end crosstalk. We send a signal into port 1, we look at the energy appearing in port 3. Because it's a tightly coupled microstrip, we would expect to see a considerable amount of near-end crosstalk. And its signature will be turning on to a small value, remaining constant, and then turning off. Let's look and see if in fact we see that in the near-end crosstalk. So that's S31 in the time domain. And sure enough, here is exactly what we expect to see. It turns on, it's relatively flat, and it turns off. Now, one thing you might ask, well, wait a minute, why don't we get near-end crosstalk right away? We send the signal in here, why don't we see near-end crosstalk right away? Why do we have to wait this amount of time to see the near-end crosstalk? Well, you can see in the physical structure, there's really very little coupling in this region. The coupling begins right here, coincident with when the line width gets narrower. And so we would expect to see that at the same time we see the reflection from the narrow line, we're going to see the near-end crosstalk appear. Let's take a look at those two time intervals. So we're going to move the near-end crosstalk over to this region so we can compare directly the timing involved. So we grab the near-end crosstalk over here, we just drag it to where the TDR is, and sure enough, now you can see that the spatial location of where we see the near-end crosstalk corresponds to the spatial location where the line width is narrower and where we have the turn on of the coupling. This is a good example of how the time domain response of the near-end crosstalk gives us information about where the coupling occurs. Information we just cannot get looking at the frequency domain response. And now we see some insight into why we have this little flat region of additional crosstalk looking at the far end. In the pink trace here, we're looking on port 4 at the far end. We saw the far end noise. Why do we get a little bit of something that looks kind of like near-end crosstalk? Well, now we see with the combination of the impedance profile and the near-end crosstalk, we see what's going on. Let's think about the dynamics of the signal. The signal is launched in port 1. It travels down this path. As soon as it gets into this region, we get some backward propagating near-end crosstalk traveling this way. Well, it gets generated in the region where we have the 70 ohm impedance. And as it's traveling along, it sees 70, 70, 70, and now it sees 50 ohm, and it goes from a high impedance to a low impedance, an impedance change. We're going to get a reflection of that backward propagating near-end noise. But because we go from 70 ohms to 50 ohms, a high to a low impedance, that reflection coefficient is going to be negative. And so as the edge moves down, as soon as it reaches this coupled region, it heads back, and now we're going to get instantly this negative reduced version of the near end crosstalk reflected, propagating in the forward direction, the same direction as the far end crosstalk. And so right behind the far end crosstalk that's propagating in the forward direction, right behind it, we're going to have the reflected near end crosstalk as negative. And sure enough, here comes the far end crosstalk coming out, and right behind it is the negative scaled down version of that near end crosstalk, reflected because of that impedance discontinuity. So we see that by looking in the time domain, we get spatial information about the impedance profile, spatial information about where the coupling occurs, and we get a feel for the dynamics of what is going on with the signal propagating down the particular interconnect. This is new information that is hard to extract directly looking at the S parameters in the frequency domain. Well, with that review of the single-ended response, let's take a look at the differential or the mixed mode response. And so to transition this data that's displayed in single-ended into mixed mode, I have a setup already created that will take that single-ended response and automatically transform it into the mixed mode response, again with my favorite orientation, frequency domain on the left, time domain on the right. So we'll recall that setup, and after it is set up, we'll recalculate it. And this setup is available for anyone to download to use themselves. This sets up the screen the way I like to see it in order to get the most out of the measured response as quickly as possible. So here is the frequency domain response for the mixed mode and the time domain response for the mixed mode on the right hand side. We looked at the mixed mode frequency domain response in the last video. We're going to look at the mixed mode time domain response right now. In the upper quadrant, I have the TDR responses, and when we look at the mixed mode response, we think of this interconnect not as two single-ended transmission lines with coupling, but we think of it as one differential pair, where we can send differential signals or common signals in and looking at differential and common signals out. So initially, we're going to look at the differential signal going in on port 1, coming back to us on port 1, or the differential signal going in on port 2 and coming back to us on port 2. And again, it's a pretty symmetrical interconnect, so I would expect to see the same thing looking at the STD11 or STD22. And sure enough, here in red and yellow are the differential TDR responses. Now, I'm going to adjust the scale so that it matches the STD11 response. So I'm going to click on the unit icon, and that will change the scale. And now we've got the differential impedance response for these two TDR responses. And you'll notice three important features. The first is it's a pretty darn good uniform 100 ohm differential impedance. When this structure was designed, it was designed pretty well to keep the differential impedance pretty constant, even though we went from a region of uncoupled to tightly coupled. So that narrower line was tweaked just right in order to compensate for the tighter coupling to maintain a 100 ohm differential impedance. And we see a pretty uniform 100 ohm differential impedance. But on top of that, we see this glaring discontinuity that corresponds to where the traces come close together, where the line width is reduced, a very large impedance change, almost 10 ohms of the differential impedance increase. Why is that? Well, when I looked at this trace under a microscope, what I found was that while the line width was decreased in this region where they're tightly coupled to maintain the 100 ohms, the decrease actually started before the coupled region. There was a small region where we necked down to the narrower line before they got tightly coupled. And if we have two independent transmission lines and we make their line widths narrower, their single-ended impedance increases, the differential impedance increases, and that's what causes this little blip over here. Now you can say, well, gee, I look at the differential TDR response from port 1, and I look and I see, yep, I have this discontinuity over here. Okay, that's the region where they become narrower and still uncoupled. And then I look at the reflection from here and it says, gee, it looks like a slightly different impedance discontinuity over there. So is there something different going on this region than on this region? Well, that's the value of having a 4-port measurement, so we can look simultaneously at the differential TDR response from both ends, because that's how you tell how symmetrical the interconnect is. When I look at the TDR response from port 2, the differential TDR response, in red, I see it's identical to what I see looking at port 1. And not only that, but when I look at port 2 and I look at this end, it's also distorted a little bit from what I see over here. The fact that both differential TDR responses give us the same behavior for this discontinuity and this discontinuity says that the behavior we see over here is because of the rise time degradation in going down that length. That in fact they're the same discontinuity. It's the fact that as that signal travels down the interconnect, the rise time is decreasing because of the series resistance and the dielectric loss. And so the rise time when it reaches this discontinuity, looking at it from port 1, it's been distorted a little bit and smeared out. And that's the value of looking at the differential TDR response from both ports at the same time. And then lastly, we see the third feature in the differential TDR response is that slight increase in impedance in going from one end to the other. And as we saw with the single-ended response, it's uphill in both directions. It's uphill looking this way, it's uphill looking this way. And that's a clear indication of a little bit of series resistance down that path. In addition to the differential TDR response, we also have the common TDR response. This isn't nearly as important as the differential response, but it's free. It's always useful taking a look at it and thinking about why we see that sort of behavior. In order to look at the units for the common impedance profile, I'm going to click on the SCC21 display, and now we're looking at the scale for the common response. And you can see we start out here at 25 ohms because we have two 50 ohm uncoupled lines. The common impedance is half of either one, 25 ohms. And in this region where they're tightly coupled, again, the coupling will increase the common impedance, it'll decrease the differential impedance, increase the common impedance, and we have narrower lines, which means even higher common impedance. And so we see the jump in common impedance from 25 ohms to 45 ohms. Again, very uniform, and then it drops down. Nothing really startling looking at the common impedance profile, but it's information that's free and provides that complete picture of the electrical properties of the interconnect. Let's look at the mix mode behavior, and that's what I have displayed in the lower quadrant. Again, there's a lot of information here, and so I'm going to click them off and we can look at them one at a time. The first example is the differential TDT response. This is the differential signal transmitted through the interconnect. And we saw when we looked in the frequency domain that the frequency domain response was really good. It was nice, uniform, monotonic. We did have that little bit of resonant coupling out corresponding to whatever that resonant structure is on port 2 at about 30 gigahertz. Very nice, clean response, a little bit of rise time degradation because of the series resistance and the dielectric loss. We can look at the common signal transmitted through as well, and our structure is a microstrip differential pair. We'd expect the differential signal to travel faster than the common signal, and so the TDT of the differential signal should come out ahead of the common signal. So let's take a look at when the common signal comes out. And sure enough, here is the common signal response. It comes out after the differential response because it takes longer for the common signal to propagate through. It sees a higher effective dielectric constant, exactly as we would expect. Now come the mode conversion terms. The first one is we send a differential signal in port 1, we look at the common signal coming back to us. And so this will give us spatial location information of where we have the mode conversion that transforms the differential signal going down to the reflected common signal. Now remember, it's a 1 volt differential signal going in, and we're looking at the common signal coming back on a 10 millivolt per division scale. So that is 1% per division. So the amount of common signal that's converted from the differential signal and reflected back, it's really small, less than 1% and less than 0.5% in most cases. And we can also use the time at which we see that common signal coming back compared to the TDR response as a measure of where that mode conversion happened. So let's move this reflected common signal into the same quadrant as the TDR response so we can compare them directly. And now you can see that where is the mode conversion happening? There's a little bit of asymmetry. Again, less than 1% asymmetry happening in the uncoupled region, very little in the coupled region, and just a tiny little bit in the uncoupled region on the other side. So that very little bit of mode conversion seems to be occurring in the launch region over on this side. And for the life of me, I look at this very closely. I can't see any asymmetry. It's a really small amount to give rise to a less than 1% of mode conversion. And the last mode conversion term we're going to take a look at is the transmitted common signal. We send a differential signal in, we look at the common signal coming out in the time domain, and that's the SCD21 term. So let's turn that one on. And now again we see nothing coming out, no common signal, nothing, and suddenly we see it coming out coincident with when the differential and the common signal are coming out. And after all, again, it's 1% per division, and so we're seeing a little bit more than 1% common signal. After all, we saw about minus 20 dB of mode conversion term in the frequency domain, and we're seeing about 1% in the time domain. Exactly where that mode conversion is happening, very hard to tell. All we can tell is that we would have this roughly 1% common signal pulse coming out of our interconnect after sending a 1 volt differential signal in. And so we see that we get different information looking at the time domain than the frequency domain, and additional information looking at both the single-ended and the mixed mode response. And that's why it's so important to have in one instrument and one user interface that integrated approach of being able to look simultaneously at the frequency domain response and the time domain response as single-ended and as mixed mode. And that's one of the innovative features that the Wave Pulsar 40iX provides.